Welcome everyone. In this video, I will be covering section 14.2, limits and continuity. The earlier section, section 1 of chapter 14, we saw what we mean by functions of several variables, functions of two variables, functions of several variables, and what we mean by level curves, and what we mean by contour maps, and so on. So this section is about limits in continuity. What does limit as xy approaching a comma b, f of xy equal to L mean? How can you show that such a limit does not exist? Before we get into function of two variables and this definition of continuity, we just recap the idea that we did in our calculus 1 class. So calculus 1 class, which was about function of single variable. So function of a single variable. So here, let's say you have a function. So something like this, let's say. So this is f of x. And let's assume that where there is a hole, let's say x equal to a. Then we say that limit as x approaching a from the right, we approach a from the right, f of x equal to, we consider this y coordinate as L, if this is L, and also limit as x approaching a from the left, f of x, so if you approach the same a from the left, so from the right, a values slightly small, slightly more than a, approach a from the left through values smaller than a, right, like that. Then this left hand side limit is also equal to L. Because these two are the same, the left hand side limit, the right side limit equal to the left limit at a. So the limit exists. Limit is x approaching a f of x equal to L, and it does exist. So in order to prove that the limit exists, we are considering two paths, right? X approaching a from the right, x approaching a from the left. We consider two paths, and for both paths, the limit value is equal to L. Only then we say that the limit exists. So it holds good even if you don't have a hole there, and if you have a solid point there, then also the same discussion holds good. So for the limit to exist, it need not, the function need not even have to be defined at the point A. You are only approaching A from the right side or the left, from the right side or the left side. We are going to take this information for function of two variables here. Limit as x approaching a, limit as xy approaching ab of f of xy equal to L means that the values of f of xy approach the number L as the point xy approaches the point a comma b along any path that is within the domain of f. Should be along any path. So in the single variable, it's along the x-axis, or you consider one side and then consider the left side limit, right side limit, and if they are same, then you conclude the limit exists. That's all it is. But in here, because we are having function of two variables, there are infinitely many curves connecting y and x, which have a relation like y equal to x square, y equal to x plus 1. There are infinitely many curves into variables. So every along any path, for any path as xy approaching AB, then the limit has to be f of xy must approach the number L. Only then we say that the limit exists. We can show that such a limit does not exist, which is easy to do. The limit does not exist by finding two different paths approaching the point along which f of xy has different limits. All you need to do is to two paths, consider two paths um, approaching the point. Then f of xy has two different limits in those two paths, then the limit does not exist. So in the section video, I would have covered problem number 9, then 13. I've done this problem number 9, 13, 17 are all done in the videos for this section. So refer to. In fact, we can do, I'll show you one problem where we'll try to find the limit, and then if it doesn't exist, we will find out two different paths over which the limit have two different values. Let's try problem number 18. Find the limit if it exists or show that the limit does not exist. So I'm going to be showing now problem number 18. So if you are going to show that the limit exists, we have to prove it in a generic way. And we cannot just choose two paths and say that, okay, in this path and in this path, the value of the limit is the same, and therefore the limit exists. So it's not enough if you just show two paths and say that the limit value is the same in both paths. If you're showing that the limit exists, then you have to prove in a generic way that along whatever path you consider in the domain of the function, then the limit are going to be the same. Then you can say that the limit exists. But if you want to show that the limit does not exist, which is easier in the sense that all you need to do is two paths, then having chosen these two paths suitably, then you have to only show that the limit in these two paths are two different values, and therefore the limit does not exist, which is what we are going to do in this problem. So let's consider the function f of xy. Which is equal to x times y to the power 4 divided by x square plus y to the power 8. Y to the power 8. Now we will choose two paths. So path 1, let's choose the easy one, along x-axis. Along x-axis, we know that y equal to 0. Along x-axis, y equal to 0. So if you consider f of xy along x-axis, because y equal to 0, you get x y to the power 4 divided by x square plus y to the power 8. So which is equal to 0. So whatever be, wherever this value approaches, whenever xy approaches to 0, 0, along the x-axis, whenever xy approaches 0, 0, along the x-axis, limit of f of xy equal to 0. Now let's try path 2. If you choose path 2, and if you choose the y-axis by any chance, then also you see, so let's try that along y-axis. Along y-axis, what is something that you know? X must be 0. So f of xy along the y-axis is x equal to 0, y to the power 4 divided by x square, which is 0 square, plus y to the power 8. So anyway, numerator is multiplied by 0, so it is equal to 0. So what are you concluding in this particular case? Limit xy approaching the origin along the y-axis is equal to f of xy equal to 0 also. So far you've considered two paths, one along the x-axis, one along the y-axis. Both values seem to be the same. Is it same for every path that you take in the domain of f of xy? Just to make sure, we'll consider just one more path and see what happens there. Path 3. So I'm going to choose the path choose the curve x equal to, choose the curve x equal to y to the power 4. The reason I picked y to the power 4 is that I see numerator involving y to the power 4, denominator involving y to the power 8. So let's try that. So along this path, when x equal to y to the power 4, what does f of xy become? It becomes f of y to the power 4 comma y. So if I substitute that into the given function, replacing x with y to the power 4, the given expression is xy to the power 4. So x y to the power 4 divided by x square plus y to the power 8. X square is y to the power 4 the whole square. I'm changing x to y to the power 4 into the expression f of xy, and we know that f of xy equal to x y to the power 4 over x square plus y to the power 8. So in this expression, I'm replacing x with y to the power 4. So you get y to the power 8 on the numerator divided by y to the power 8 plus y to the power 8, 2y to the power 8. So because now xy is approaching 0, 0, x is approaching 0, y is approaching 0, but it's not equal to 0. So when you consider limit as xy approaching 0, 0 of f of xy, so you get y to the power 8 here, y to the power 8 here. Limit as xy approaching 0, 0 f of xy. What it means is x approaches 0, y approaches 0. But we know that it is y to the power 8 over 2y to the power 8. As y is not equal to 0, it can cancel like that, which is equal to 1/2. So we notice here, along the x-axis, the limit is 0. Along the y-axis also, the limit is 0. But along the curve x equal to y to the power 4, the limit is equal to 1/2. So what did we say initially when we said that the limit does not exist if you find two paths along which the limits are different? So we have found out two paths. The x-axis is one path and the other x equal to y to the power 4. These are the two paths. So along x-axis and along the path x equal to y to the power 4, we have the limits to be two different values, namely 0 and 1 half. So as the limits are not the same along two different paths, the limit does not exist. Limit of f of xy as xy approaching 0, 0, um, uh, limits of f of xy, so xy approaching 0, 0, are two different values along two paths, and therefore the limit does not exist. So the limit does not exist. So what are the two paths in this particular problem? Either you can say y-axis and the curve x equal to y to the power 4, or you can say x-axis and the curve x equal to y to the power 4. There are two paths. Give two different limits. The next concept here is the continuity. What does it mean to say that if f of two variables is continuous at AB? Again, it is similar to the definition of calculus 1 material. So we say that in single variables, calc 1, so if y is a function of f of x and it is said to be continuous at a, if limit as x approaching a of f of x equal to f at a, if this happens, then f is said to be continuous at x equal to a. This is the definition. So what it means is the limit should not only be existing, it should also be equal to the value of the function at a. Exactly similar concept here. A function f of two variables is continuous at the point ab. If limit as xy approaching ab of f of xy equal to f of ab, the value of the function at AB. The limit exists, and also the value of the function should be equal to the limit at that point AB. If f is continuous on R2, what can you say about its graph? If f is continuous on R2, the graph will appear as a surface without holes or breaks. So it's again similar to the idea of continuity in single variable. In single variable, so that the graph is said to be continuous if you can draw the graph without lifting your pencil. So it means that whenever you have a point x equal to a, and if you allow x to approach a from the right and x approaching a from the left, this is a plus and this is a minus. They should be equal to the limit L, and also the value of the function should be equal to L. So limit as x approaching a of f of x should be equal to f of a, and that should be the limiting value as well. So there is no, if the graph is continuous, there is no break or hole in the graph. That's exactly similar because it's function of two variables. Instead of function, we say that the graph is a surface. So f is continuous on R2. What can you say about its graph? The graph will appear as a surface without holes or break. So again, problem number 37 is also done in the video section, the video part. So please take a look at this problem in the video. The videos for section 14.2. So in this section, mainly what we mean by limit, when do you say the limit exists? When do you say the limit does not exist? And the definition of continuity. And then check the problems that I have done based on these concepts in the videos for section 14.2. Hope these videos help.